Okay, so whenever you want to discuss some questions, so please tell us about that and we can arrange for
Yeah,
that.
I have one doubt from quadratic equations.
Oh, good. So from the NCRT or from the assignments?
Not from the assignments. It is from this reference book. Um,
Oh,
no, but that's also there in NCRT too.
yes. Which chapter, which exercise?
Once, I'll tell the question.
Yeah.
Yeah, it is if if x is equal to -2 is a common solution for quadratic equation. No, not this one. Yeah, yeah. If one of the root of the equation k minus 1x square minus 10x plus 3 minus 10x
Minus, minus 10x plus. Right. This is the quadratic equation. Yes.
is the reciprocal of the other, find the value of k.
Okay, so one of the roots is alpha and the other root would be how much?
Reciprocal of the other, so 1 by
Yeah, 1 by alpha, right? And we know that what would be the sum of the roots, right?
some of the roots is alpha plus beta equal to minus
And
b by.
that, yeah, and that would be minus of minus 10 by k minus 1. So this is one thing which is 10 by k minus. Similarly, we can also calculate what is the product of the roots. So this I guess we will not. What is the product of the roots?
Alpha and beta equal to c by a. So
3
3
by
by
k,
k
right?
minus 1.
So this cancels out. So we have 1 which is equal to 3 by k minus 1. So this goes in this side. So k minus 1 is 3. So k is, yeah. So, is this clear?
Because this question is, because it was a little confusing. It was because this
Yeah, yeah, of course.
polynomial is that, right? So
Yeah,
alpha
yeah.
beta.
Mhm. Yeah, so no,
Um
no problem. Yes.
and also one more doubt. In this quadratic equation,
Okay, so Arsalan is here. Okay.
when we have to use
Arsalan,
a bit
please.
value, right?
Yeah, please wait a moment, Arsalan. Okay, it's okay. Please, right?
Okay, sir.
Yes, what is the problem, Rifa?
Yeah, in the quadratic equation, to find the solution, we can to find the solution of the quadratic equation, we can use any method, right? Like
Yeah, yeah, of course, any method. Whether it is middle term splitting, whether it is a quadratic formula, depending upon yeah, which method you are comfortable with, so you can use it, right?
okay, yeah, that's it.
Good, good. So all the best, Rifa, and only one thing to remember: don't panic, don't take too much pressure, relax, and then prepare well, and then give the. Okay.
Yeah, okay. Thank you.
Bye, bye,
I'm
bye,
not
Rifa. I love this. Bye. Okay, yes, Arslan. Assalamu alaikum.
Assalamu alaikum, sir.
Walaikum salam, walaikum salam. So we finished this chapter, right? So
Hmm.
now I wanted to start from the first chapter, but Mir is not here. So I will start the first chapter when Mir is around, right? Mir Hassan. So I will talk about those chapters when Mir is around, right?
Yes, sir.
Then let us start with this. Or should I start with the first chapter? So let us do this second chapter, eighth chapter, and then when Mir will be available, then we'll start this first chapter, which is the charges, electric charges, and
Yes, sir.
yeah. So the after AC, the next chapter is electromagnetic, right? By this one, right? Electromagnetic. And the first topic is Maxwell equations, right? Okay, so or I should write Maxwell equations. So Maxwell was the guy who was able to connect both the electric property of the charges and magnetic property of the charges together. He was a brilliant scientist. And he was able to join all these properties together, and he gave this Maxwell equation, right? Yeah. So we have not done these previous chapters. The first two chapters, which were about charges, electric fields, and second chapter was this potential and capacitance. Third chapter is moving charges and current and magnetic field. Fourth chapter is magnetic field, and the fifth one is magnetism and matters. And the sixth one is electromagnetic induction. Seventh one we did with you AC, and this eighth one is this electromagnetic fields. So when you combine all these previous chapters, six chapters, so combinedly this Maxwell gave all these set of equations, right? So before we do that, first let us go back to what is the current that you define? What is the current? What is the electric current? Arsalan, what is electric current? Okay, you don't, yeah, you didn't do this third chapter, but you have done this in your 10th class. What is current?
So electric current is basically like charged particles, right?
Yeah,
Flow of the
charge
charged
part,
particle.
flow of charge. Yeah, absolutely right. So whenever whenever there are charged particles which are moving, right? So whenever you have these rate of, so current is defined as, yeah, so electric current that we have studied. So yeah, we didn't study in the third chapter, but we'll do at some point. So electric current is defined as rate of flow of charge, right? So let's say there is this charge, which is, let's say this is a negative charge, electron which is traveling. So if this is moving in this direction, then you will have a current in this direction, right? So then there will be this conventional current, right, Arsala? Yeah, but we'll do this electric current in detail in the third chapter. So when I will start the backup class, right, with Meet, which will happen soon. And in that class, I will start from this electric charge or the static charge, charges at rest, and then moving charges. First, we will do this, and then we will do this moving charges. So in moving charges, we will talk about this electric current. But Maxwell also showed that, so he found out that, yeah, so there is this law which is called the Ampere circuital law, right? So Ampere circuital law says that whenever you have a flowing charge, right, and then there is some current which is passing, then you can calculate the, yeah, then you can calculate the magnetic field using this Ampere circuital law. So this Ampere circuit law, again, you will study this in the third chapter, electric current. So this, not in the third chapter, but in the fourth chapter, in magnetic fields. So this is defined as B dot ds, and this is equal to mu naught and I in, right? So this is the Ampere circuit law. You take an Amperian loop, right, in which from this surface, this current is passing, right? So you have this circular thing, circular Amperian loop, and in this surface, this current is passing. So you can define this magnetic field at this point. You can calculate this magnetic field using this Ampere circuit law. So this we will do. Just take this thing as for granted for now, but we will do this thing in the fourth chapter. Okay. Yeah. So this is the Ampere circuit law, right? Which says that if you want to calculate the magnetic field in this closed loop, right? So this is a closed linear loop, right? This is a closed line integral. And in this closed loop, if you calculate this B dot magnetic field dot this length, small length, and this would be equal to mu naught and this I input. So whatever I is crossing through this circular, right? This is called the Ampere circuit. But what Maxwell found out that let's say we have a capacitor, right? So we have a capacitor, and this is the current which is flowing. So current is flowing in this, right? So when this current is flowing, so there would be this positive charge created at this point, and there would be this negative charge, right? So is there any current, any charges flowing in this direction inside this capacitor?
Uh,
Any charge which is flowing inside the capacitor?
yes, sir.
No, there is no any charge, right?
Can you explain how?
Because the charges are flowing, can flow through the conductors, right? And
Yes, sir.
this
Isn't
is
the
the one.
capacitor like part of it? So, in a way.
Yeah, capacitor is a device which is made up
Mm-hmm.
of two plates, right?
Yes,
So
sir.
between the plates, there is no movement of charges, right?
Also,
Just,
so you mean
yeah,
between the, okay.
yeah, between the
Yeah,
plates,
okay.
because I have not
Okay.
written them. So you see that these are the two plates, right? It contains the positive charge, and there is this plate which contains the negative charge, right? But the charges are not traveling from this part to this part, right? They are not
Hmm.
traveling, right? So yeah, this is, so there is no movement of charges inside this capacitor, right? And if we don't have any movement inside the capacitor, which means that there would be no charges, there would be no current inside the capacitor, right?
Hmm.
So then if I want to draw, or if I want to use the Ampere circuit law, and if I want to calculate the magnetic field at this point, right? So I have to make an Amperian loop. That is the idea, right? From the Ampere circuit law, we know that if I want to calculate the magnetic field at this point, then I'll have to make an Amperian loop, open surface, this surface, in which this current is passing, right? So
Yes, sir.
if I want to calculate the magnetic field at this point, I make an Amperian loop like this, right?
Hmm.
In this surface, this current is passing, right?
So only the current that like passes the surface, that's the one that's
Yeah,
calculated. Okay.
yeah. So that will give the magnetic field, right?
Okay, sir.
So this, let's say this is point P, and this I say as case one. Okay. So if I use the if I use the Ampere circuital law for case 1, and let's say this radius is r, right? This radius is r. Okay. So for case 1, if I use the Ampere circuital law, this would be V dot dl and mu naught, and I enclosed is I, right? So let's say I enclosed. So this would be V dot dl, and this is mu naught I, right? Because
Mm.
there is a current which is passing through this surface. Okay, is this clear?
Yes, sir.
So this is case 1, right? Now take another case. So if we take another case, right, and if we make the surface like this, so this is the current which is passing, right? And if I make a surface like this one, so this one and this one, so this surface is like this one. This is a bottle type surface where these are the surfaces, right? So this is the surface. So surface is this one, the curved surface of the bottle, right?
Mm.
And the mouth of that bottle is open, right? So the mouth of this bottle is open. So is there anything, any current flowing through this area,
No, sir.
right? So if I write the Maxwell or if I write the Ampere circuital law, right? So if I write V dot ds, and if I write mu I enclosed, so how much is the I which is enclosed in this surface? Is there any I?
Mm. No.
Because this is the open
Yeah.
surface. So this
Yes,
is the
sir.
open surface. Let me show you that. So let me, this is not the bottle that I have, but just make you one. So this is the open, right? And the current is going inside, and this is not passing through this surface because this surface is not closed, right? If in the earlier case I took this surface, which was this open surface, right? So from
Mm.
this surface the current was passing. But if I take the open surface, so now the surface is this one. This one is the surface, the this outer region, right? The curved surface. So in this curved surface, there is no current which is passing, right?
Yes, sir.
So if there are no current which is passing through that curved surface, which means that this would be zero, right? So if I calculate this V dot ds, then I will get the magnetic field at P point, which would be zero. Is this part clear?
Yes, sir.
So in the earlier example, right, in the earlier example, when I calculated the magnetic field, so there was this value of some magnetic field at P point, right? That was non-zero because there was current which is flowing in that surface, right?
Mm.
And in the second case, when I make the surface like this bottle, right? So this is the now surface. So inside this surface, there is no current which is passing,
Yes, sir.
right? So then there is no magnetic field at this point. So I am using the same principle. I am using the same Ampere circuital law, right? And this is giving me two different values, which means that there is some discrepancy in the laws of this Ampere circuit law, right?
Yes, sir.
Right. So it is showing me that there is some discrepancy in the laws, but this should not happen, right? The law should be correct, right?
Yes, sir.
And again, we can take another example again. So let's say we have the case third case, right? And again, I have this surface. This is again the open one, and the current is passing through this one. And I take a tiffin kind of. So I take a tiffin kind of this, right? This is the tiffin that I have. So now this is my surface, right? There is no current passing through this region, and there is no current passing inside this surface, right? So
Yes, sir.
again at this point, when I use this Ampere circuit law, right? So again, when I use this V dot dl, and this will be more clear when you, so when I will teach you this fourth chapter. This Ampere circuit law is in the fourth chapter. So when I'll come to that chapter, then it will be more understandable. But you just take these things for granted now, right? So I enclosed. And then again, there is no I because I enclosed is 0 for this case because no current is passing through this surface, right? There is no current inside the capacitor. So then this would be 0. So again, I will get a magnetic field at P point, which is 0, which is absurd. So this should not happen, right? So then Maxwell found out that Maxwell told us that there is this, so the current does not happen only when there is flow of charges, right? So
Yes,
in,
sir.
yeah, so he showed us that when we change this electric flux, right? So change in electric flux also produces some current, right? Which means that there would be some current inside the capacitor as well, right? There are
Yes,
no
sir.
charges. There are no charges flowing inside the capacitor. But what is happening inside the capacitor? So let us see what is happening inside the capacitor. So we have this capacitor,
Hmm.
and we have this positive plate, right? And we have this negative plate. So do you know what is the electric field inside the capacitor? Do you know?
So there is no electric field inside the capacitor, right?
Yeah, there is some electric field,
Oh,
right?
yeah,
There is some
electric.
electric. Yeah. So okay. So again, we'll have to go back to the first chapter. So these are two plates, right?
Hmm.
And you will understand that for the case of this positive plate, so the electric field would be, let's say this is positive. So the electric field would be coming out of this circuit, right? And
Okay,
that
sir.
is equal to sigma by 2 epsilon naught. So that is the amount of electric field for the case of positive. This you just take this value for now, and when we'll do the first chapter, then this would be easy to understand. Okay.
Okay, sir.
So similarly, you have a negative plate, right? This is the negative plate. So you have this negative plate, and for the case of negative plate, electric field magnitude is same. Only the direction is different. So for the case of negative plate, the electric field is coming towards this negative plate. For the case of positive, the electric fields are going outwards, For the case of negative, the electric fields are coming inwards. So this we have to remember. Okay. And electric field is a vector quantity, so they will add like vectors. Okay.
Hmm.
Yeah. So now we have to find out that what would be the electric field inside the capacitor. So let's say that we have this positive plate
Yes, sir.
and we have this negative plate. So we know that for this one, the electric field is in this direction.
Yes, sir. And the other is in the
Yeah. So
opposite.
this is sigma by 2 epsilon. And for this is this side, this is this one. That's sigma by 2 epsilon. So this is E positive, and in this direction also we have E positive, which is sigma by 2 epsilon. Right.
Hmm.
Now for the case of this negative one. So for the case of negative one, the electric field would come towards this plate. Right. So what would be the direction? So this is in this way.
Yes,
Right.
sir.
This is E negative coming towards this plate. And in this region, it is coming towards this plate.
Sir, I have a doubt.
Yes, yes, of course. Yeah, what is the doubt?
Sir, on the negative plate, as you
Yes,
can see, the arrows are going towards the negative plate. So,
yes.
sir, what happens when you know, in the lower one, why do the arrows like now go away? Shouldn't the arrows on this side go towards the negative plate?
Yeah, so you're talking about this region.
Yes, sir.
Yeah, so
Why
this
aren't
arrows would be coming towards it. Yeah. So this is E negative, right? So this is contribution for E negative, right? Sigma
okay,
by
sir.
2 epsilon. This is again sigma by 2 epsilon. And this is again sigma by 2 epsilon. So these yellow ones are the contribution for the negative plate because all these electric fields are coming towards this plate, right? For the case of the positive plate, all these arrows are going away from this plate, right?
Mm.
It, is this part clear?
Yes, sir.
So let's say that if I tell this one as the first region, this is second region, this is third region. So in in which regions or maybe region, these electric fields are cancelling out, and in which region they are they are collaborating or they are adding up,
Sir, in the middle region, they're collaborating, and in the other regions, they're like going.
cancelling out, right?
Yes, sir.
Yeah. So in the middle region inside the plate, they are adding up, right?
Mm-hmm.
And in the first and second region, this is going in this way, this is going in this way. So they are going in the opposite direction. And if we add those two vectors, then this will cancel out. This will cancel out, this will cancel out. So we have
Mm.
electric field inside this region. So total electric field would be the adding up of these two electrons, right? E plus E minus, right? So this is
Yes, sir.
sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So this would be half plus half, so this is 1.
Yes, sir.
So now this is the electric field inside the plate, right?
Mm.
And the direction you already know. So the direction is in this, so what is that? So the direction is in this direction, right? Correct.
Mm.
Okay, so we have this electric field, and now what did I say earlier? That if we change this electric flux, or if we change this electric field, then this will produce some current. So let us find out that what is that. Okay, so we have these two plates, right? And these are the electric field which is passing through the surface. This is sigma by epsilon naught. This is positive plate and this is a negative plate, right? So E is sigma by epsilon naught. And if I calculate E into A, what is electric flux, right? So electric flux would be how much? That would be E into A, right?
Yes, sir.
And E I know. E is sigma by epsilon naught. And this is A. So what is sigma into A? What is this sigma? Sigma is a surface charge density, right? So surface charge density means that what is the amount of charges which is placed in this area. So right, so this means that how much charge is there in this area. So that is the surface charge density. So that would be sigma would be charge in an area, right?
Yes, sir.
Is this part clear?
Yes, sir.
Yeah, so if I calculate sigma into A would be how much? Charge.
5. Sir.
So this is sigma into A, that is Q, and this is epsilon naught. So if I write phi, so that would be electric flux, which is Q by epsilon, right? And then what I do is that I differentiate both the sides with respect to t. Okay. Then this would be d by dt of phi e, and this is d by dt of q by epsilon, right? Epsilon naught is the permittivity of the free space, right? So
Yes,
this is
sir.
so this is constant, right? So this is d phi e by dt, and I can take out this epsilon naught outside, and this is dq by dt. What is this dq by dt? Rate of flow of charge.
Mm.
That is the current that I defined, right?
Yes, sir.
So this current, let me just name it as D, right? And this is du phi E by D.
Sir, I have a
This,
doubt.
yes, yes.
Uh, let's say once again. How did
Yes, yes, sure, sure.
D by dt into 5 by E naught become 1 by E naught into dq by
Yeah,
dt?
yeah, of course. Of course, of course. So let's say this is 1 by epsilon naught, let's say D by dt of, let's say, 5 q, right? So this is a constant 5. So I can take it outside, right? Constant, I can take it outside. Similarly, I have a constant which is, let's say, q by 3. So I can take out 1 by 3, and this would be, so this is the constant, 1 by 3, right? Is this clear?
Yes, sir.
So similarly, I have this constant, so I have taken this constant outside the differentiation, right? So then this is dq by dt. Now, the rate of flow of charge is called the current, right? But actually, there are no charges which are flowing. But due to this change in electric flux, so you see that this electric flux is changing over time. So that will produce this current, which is called the displacement current. So if I calculate this ID, so that would be epsilon naught d phi E by d. So this is called the displacement current. So this is what Maxwell suggested or Maxwell discovered, right?
Okay, sir.
So, so due to the change in electric flux, there are no charges flowing inside the capacitor, but there is some change in electric flux, right? and due to the change in electric flux, there are some current which is flowing also inside this capacitor, right? So if I, yeah, so if I consider that there is some current which is flowing inside the capacitor, then I enclosed would be that I current, right? Then this Ampere circular law would be fine. Is that clear?
Yes, sir.
Yeah, so we will understand about that Maxwell correction, but let me write the displacement current first. So what is this displacement current? So the current generated due to change in the electric flux which is pi e over time. Right, so if there is some change in electric flux, so then there would be some current which is called the displacement current. So then that current is called the displacement current. Right, and it is denoted by ID, and this is equal to epsilon naught d pi e by d. So please write. So any doubt that you have up until now?
No, sir.
Yeah, this would be become more clear when we do this first few chapters, right? First 6 chapters when we'll do that. So then this would become more clear, right? Because you didn't know this Ampere circuital law, you didn't know this magnetic field, this I enclosed. So when we'll understand these things, then it would be more right.
Mm.
So please write from this point. And if you have any doubts, so please ask that.
So can you scroll down?
So
Yes, sir. Yes, sir. Scroll down. Yes. Wait, sir, I didn't read this one. I didn't draw the diagram. So can you scroll down? So can you scroll down? So can you scroll a bit up? Just looking at one. Oh yes, that's done. Yes, sir, that's done. Yes, sir, scrolling. Yes, sir, this.
Yes, noted.
Yes, sir. 1 second. Yes, sir. Scroll down, scroll.
Yes, these are the equations that you're solving.
Sir, scroll down. Yes, sir. I'm done.
Then the last part, which is
Yes.
displacement.
Yes, sir.
It,
Yes,
okay,
I'm done.
good. So now we saw that there are two kinds of current, electric current, and those are, so one is due to flow of charge, right? And that we call as the conduction current. And then the other one, which is due to the change in electric flux, and that we call as the displacement current. So there are two types of current. So the general idea would be this, that we have a supply, right? And this is not a constant supply. So let's say we have this change in supply, and then we are, so this is capacitor, right? So let's say this is the flow of charges, which is the conduction current, and inside this capacitor, so there would be no conduction current. So IC would be zero, right? And then again we have this IC. But inside this capacitor, we have this displacement current, right? But in here, the displacement current is zero. In here, the displacement current is zero. So is this part clear?
Yes, sir.
And then Maxwell wrote this correction. So correction in ampere circuit law. So if we write B dot ds as mu naught and IC, which is the conduction current plus the displacement current, right? Then this would be mu naught IC is I, and this is epsilon naught d phi by d. This is the correction that is given by. So this part is the Maxwell correction, right? And then
Hmm.
this would be mu naught IC plus mu naught epsilon naught d phi by d. So this is the corrected ampere circuit.
Yes. So, sir,
Again,
like,
yeah.
why didn't we just learn this directly? Why did we have to learn, the previous one? Just learn the corrected one, right?
The incorrected one, yeah, because in the third chapter you will see that there is. So we didn't study about the idea of this displacement current, right? So we didn't talk about, or we didn't need this current inside this capacitor, right? But when Maxwell saw that, yeah, there is some need in this. So there is need of this current inside the capacitor. Then we understood that we have to make some correction in the Ampere circuit law, because Ampere circuit law was perfectly fine for the conduction current, right? It is
Yes, sir.
perfectly fine for the conduction current. This has a discrepancy when we have this displacement current, right? So in the third and fourth chapter, you will see that all the devices are using this conduction current, right? Then we don't need this correction. But whenever we are using this capacitive and all these things, then we need this idea of this displacement. So that is where this correction is. Okay, because let's say we are talking about this wire, right? This is the wire, and let's say we are talking about this circular wire, right? And the current is full. And let's say we talk about, let's say we have this sinusoidal wire. So all these wire in which the current is flowing. So is there any other thing in which there is this displacement current? So in all these examples, the charges are flowing, right?
Hmm.
So then we don't need this idea of displacement current, right?
Yes, sir.
Yeah, so that is why we use this uncorrected or incorrect ampere circuit, because at that point, whenever we have these circuits, right, these wires and all these things, so in those wires we have these conductors, and they carry free electrons, and then we have these flow of charges. So then we have only this conduction current. So then we don't need this displacement current. Yeah,
Yes,
that is
sir.
why this incorrect one is also important. Whenever we don't have any displacement current, that is zero, then we only use this ampere circuit.
Okay, sir.
Okay, so please note down this part. So that was the correction. And in this next class, I will talk about, yeah, so tomorrow there is this class with the batch that I am teaching, right? So in that, I will talk about
Hmm.
this light optics, but with you, I will take the backup. Right?
Hmm.
Yeah, whenever you want me to
Yes,
slow
yes.
down.
Can you scroll?
Yeah, so in the fourth chapter, we will talk about the magnetic field using the ampere sector. So all these kinds of right. But in that, we will not use this corrected one, right? We only use this.